You often hear about climate change in the news, with scientists talking about things like global warming. While the science behind climate change is very real, there are consequences beyond just those of nature, with important implications to humans, society, and the economy. In today's economy, market failure and climate change often go hand in hand, and if left uncorrected, the impacts of climate change can be costly.
So before getting into specifics, it is important to point out that there is a difference between global warming and climate change. While temperature increase does play an important role in our Earth's changing climate, climate change involves many different complex interactions between the sun and our Earth's oceans and atmosphere. Incident solar radiation warms the Earth's surface and is emitted back to the Earth's atmosphere in the form of infrared radiation. A number of atmospheric gases, including water vapor, carbon dioxide, and methane, absorb this radiation and cause an insulating effect, leading to an increase in the temperature of the Earth's lower atmosphere. This is known as the greenhouse gas effect due to the insulating effect of these greenhouse gases.
Although it is true that CO2 concentrations have varied cyclically throughout history, evidence shows that in the past century, CO2 increase has occurred at an unprecedented rate, with current levels far exceeding any pre-industrial levels. In order to see the increased concentration of CO2 in the atmosphere, Princeton has created a model in which you can picture the Earth like a bathtub. Picture the faucet adding in 8 billion tons of human-induced CO2 annually, and picture two drains in the tub. The oceans, which can remove 2 billion tons annually, and the land biosphere, which can also remove 2 billion tons annually, for a total of 4 billion of the 8 billion tons input being removed. The remaining 4 billion become concentrated within the atmosphere for a net of 4 billion tons added every single year. Now if you look over here, during glacial periods, there was a total of 400 billion tons in the bathtub. During pre-industrial times, it was at 600 billion tons. After industrial times, today we are at 800 billion tons annually and increasing a net of 4 billion tons every year. The concern is that we will double these pre-industrial levels from 600 billion tons to 1,200 billion tons. The goal is to keep it at 800 or even reduce it if possible. Through direct measurement, it is easy for us to quantify current levels and trajectories of atmospheric CO2. We are also able to measure past concentrations of CO2 through the use of proxy data, in which indirect evidence is used as a substitute for direct measurement. For example, Arctic ice that has been accumulating over geologic time contains small air bubbles containing atmospheric gas from long ago. Through the drilling of ice cores and observation of the chemistry of these ancient bubbles, a timeline of atmospheric gas concentrations can be constructed. The oceans also absorb CO2, and as atmospheric CO2 concentrations rise, so does ocean absorption. This process alters the chemistry of the oceans, known as ocean acidification, and has numerous adverse effects on marine life. Similar devastating effects can be seen across a wide array of terrestrial and marine ecosystems alike. Climate change does not only pose a risk to the natural environment, but to human health and society as well. For example, an increase in Earth's average temperature could lead to the geographic expansion of tropical diseases. There are also a number of respiratory ailments associated with smog and other conditions resulting from a combination of pollution and temperature increase. Increased storm magnitude can lead to an increased risk of injury or drowning, and flooding can lead to a number of sanitation problems as well.
Many people's livelihoods would also be affected by an increase in temperature and changing climate patterns, including those in industries such as agriculture, forestry, recreation, and a number of others. Sea level rise is another major concern for human health and well-being. As global temperatures increase, polar ice caps continue to melt at a rapid pace, leading to an increase in sea level. This increase, combined with an increased risk of storm surge, could require the relocation of hundreds of millions of people living in coastal regions. Because of the dynamic and interconnected nature of Earth's processes, it is difficult to assess exactly what the extent of what climate change would be. Climate processes are often subject to feedback loops, which are systematic, circular processes in which the output of one process acts as the input of another, resulting in an amplifying or minimizing effect throughout the process. The Intergovernmental Panel on Climate Change, or the IPCC, is an international body tasked with reviewing and summarizing the extensive amount of available climate data. Based on their multi-annual reports, assessments can be made as to the current state and predicted future impacts of climate change, including the associated potential economic burden.
Numerous scientific models have been created to utilize available climate and emissions data to estimate the likely future effects of human-induced climate change. Integrated assessment models can then combine these with economic models in order to estimate the annual expected burden of climate change on GDP. Current projections estimate that if left unchecked, the annual financial burden could be as great as 5% of GDP annually, with the potential to increase as time goes on. In order to reduce the impact of climate change as much as possible while not devastating the economy, as well as increasing social welfare as much as possible, it is necessary to find the optimal level of pollution and abatement. This optimal outcome can be found where marginal abatement cost of one more unit of pollution is equal to the marginal damage of one more unit. If you look here on this figure, the y-axis represents cost and the x-axis represents the increase in emissions. This line here can be seen as the marginal abatement curve, and it shows the level of cost coming with each unit of abatement with each increasing unit of emissions. The marginal damage line here shows the expected damages to incur with each unit of emissions. The optimal can be found right here at the intersection of these two curves. The social cost of carbon is the expected cost or damage to society in present value of 1 ton of emitted CO2. Because many of these costs will be dealt with in the future, it is necessary to discount from the future in order to consider personal temporal value and determine the present value of future investments.
Because of difficulties predicting the magnitude and timing of climate change-related costs and their impacts on social welfare, decisions must be made as to what weight is put on present response versus future response. In a long-term investments such as those needed for climate change mitigation, impatience and risk factors require future expenses to be viewed in present value for comparison, and decisions must be also made as to what generation should bear the burden of cost. In order to do this, a discount rate must be chosen in which the interest rate used to determine the present value of these future investments. If a higher discount rate is chosen, lower present value is put on future investments, and more weight is put on the present. Therefore, a higher discount rate calls for early action to be taken, while a lower discount rate calls for future action. Along with climate change comes numerous negative externalities, as well as issues related to a lack of well-defined property rights resulting in market failure. To correct market failure, government intervention is needed, and in the case of climate change, that comes in the form of command and control practices, or market-based strategies such as carbon taxes or cap-and-trade systems. Command and control regulation has been the dominant form of pollution regulation to date. This involves the use of non-market driven government mandates, explicitly stating what pollution levels are acceptable and what is illegal. Although, as we have seen, these means of regulation are often inefficient and difficult to regulate. Another weakness of command and control policies are their lack of incentive for future innovation and emissions reductions beyond what is explicitly stated.
In a cap-and-trade system, a cap is set to designate the maximum allowable level of emissions for an industry or a region. Through a system of permitting, polluters can receive a number of permits, each of which can be used for a certain unit of emissions. These permits may be given or may be auctioned off. The sum of the emissions allowed by these permits equals the cap. Each polluter can then decide independently the most cost-effective way to stay within the cap. Some companies can cheaply and effectively abate pollution to well below the cap, while others find it cheaper to pollute beyond their cap by purchasing excess permits not needed by the previously mentioned companies. This creates a competitive market for emissions trading and incentives for polluters to either reduce emissions or invest in greater abatement capacity.
A carbon tax involves placing a direct cost on each unit of pollution. By placing a tax on emissions, the government can ensure that in order to act as efficiently as possible, polluters will continue to abate until the cost of one more unit of abatement costs more than the carbon tax, in which case they will pay for the tax. This process ensures the optimal level of abatement is reached through market mechanisms.
Through economic processes, both carbon taxes and cap-and-trade systems reach the optimal level of abatement, reducing total damage and increasing social welfare, while also ensuring the equitable level of cost-effective abatement between polluters. Both regulation strategies share three main benefits: a reduction in emissions to the optimal level, incentives for innovation for polluters, and creation of government revenue, although they do not necessarily have to create government revenue. The main difference between these market systems is where the burden falls, with the burden falling more on firms in the case of cap-and-trade systems, focusing more on the main polluters, while a carbon tax is shared amongst all of society.